Thank you very much. Well, thank you to the organizers for this very nice workshop. So I also have to apologize that I'm not talking about low regularity space-time, although towards the end, there will be an application to something that is not standard smooth geometry, and there will be a Sobolev space or two. So at least there's something with lower regularity. And I should also say, to start with, this is not some sort of ecological talk. We are talking actually about Green, George Green, and as I'm sure you all know, he was, before he started on electromagnetism, he was a miller. And this is in fact the windmill where he worked, although strictly what you see is the bounding surface of the windmill. And if you want to know about the interior volume, well, there's a formula for that, which Green gave us. Okay, so this is going to be about green hyperbolic operators. And this is a theory introduced by Christian Baer a little while ago, and it somehow formalizes everything we already knew about green operators for hyperbolic operators, makes it a bit axiomatic, and actually shows you get all of the analytic information out of some algebraic definitions. So to set the scene, we have a globally hyperbolic space-time. We have maybe some vector bundles, finite dimensional, over this space-time. And let's start with a partial differential operator. Eventually, we're not going to be dealing with partial differential operators, but we start with one. So this goes between smooth sections of one of these bundles to smooth sections of another one. And then it has a formal dual based in a very obvious way, okay? And we make the following definition. So a green operator for this partial differential operator is a map, E plus or E minus, going from the compactly supported sections of one of these bundles. Again, actually this should not be to the compactly supported ones, this should just be to smooth sections of the other bundle. And there are three conditions. One, it acts as a solution operator to the equation that we're interested in. The other, well, it's a sort of turned around version of the same equation. So this is a green operator on both sides. And in particular, we have the support property here that when we feed in a compactly supported section into one of these operators, the support of what comes out is in the causal future or past of the original support. So here's F, and there's the causal future of it, and there's the causal past. And so this is the retarded, and here is the advanced solution. So what is a green hyperbolic operator? It's simply a partial differential operator P, which has green operators for P and green operators for its formal dual. Okay, so that's the idea. And notice this is essentially algebraic. The other thing to say is this is not in some ways a general, well, these are not always hyperbolic operators, because one of the main examples of a green hyperbolic operator is the Klein-Gordon operator, okay, which is normally hyperbolic in dimensions 2 and above. In dimension 1 plus 0, then of course the Klein-Gordon operator is just d2 dt squared plus m squared, which is what you would normally think of as an elliptic operator. Okay, so, but this is green hyperbolic because you can solve and find a green operator that obeys retarded conditions, okay, and also one that obeys advanced conditions. So this is an elliptic but green hyperbolic operator. So now the point, this is algebraic. This is sort of some sort of two-sided inverse property and then a support property. And the other thing we're doing, we are not at this point assuming anything about the uniqueness of these operators. We just say they should exist. Okay, so there may be many. The remarkable thing that Christian Baer showed was that this algebraic definition has analytic consequences. And I'm not going to go through those now because at a later point there'll be a generalized version and then you'll see how it all goes. Okay, so what I'm going to do is take this theory of partial differential operators and generalize it a bit. And I'm going to generalize it beyond differential operators altogether to actually operators that have some non-locality. which seems like a strange thing to do, and I indeed would not have done it if I had not had a reason for doing it. So that it actually comes out of another project that I might mention at some stage. But let's see why you might end up wanting to look at some non-local equations. So let's just consider a coupled linear system, and let's let P and Q be Green-hyperbolic operators, and the off-diagonal pieces, let's suppose that they map smooth functions to compactly supported functions with support in some particular K, right? And there are situations where this might turn up. So one way of addressing this would just be to go to a book which tells you how to deal with systems of equations. But another thing you might do is say, well, normally what I do when I have a system of two equations is I try to decouple them. So let's see what happens if you decouple them. And you can. So this is the decoupled system. Notice we have an equation for phi only here and some modified source. And these are equations you get if you assume that you're looking for a solution that is either retarded or advanced in terms of its boundary conditions. So you get this system here, so it's decoupled, but notice that what we have is a non-local operator here, because S might be a partial differential operator, for example, but the green operator that gets sandwiched in there is most definitely not a partial differential operator. So this is non-local. So naturally, we end up with a non-local equation on our hands, if we want to solve the system this way. But there are also other motivations for doing this. As I said, this came out of a project which was actually about measurement in quantum field theory. And one of the standard examples that's used in this theory is the so-called Unruh-DeWitt detector. And in this situation, you have a quantum field, and it is coupled to an oscillator, okay? And, well, quantized in both cases. And then you try to see what excitations are there of this quantum mechanical system induced by the quantum field. This is a very important model in quantum fields in curved spacetime. So I've written down the equation of motion here. Phi, the classical equation, phi is going to be our scalar field, and psi is going to be the oscillator. Okay? And we have the idea that the oscillator more or less follows this trajectory, gamma of tau, and we couple them together by saying that the oscillator senses the pullback of the field, the scalar field, onto that trajectory. Okay? So that's this pullback here. And then dually, the field senses the push forward of the oscillator variable out into the space-time. And this, of course, is distributional source for the field. Now, the interesting thing for our current purposes is that this is actually a non-local partial differential equation, because the scalar field and the oscillator obviously belong to the direct sum of smooth functions on the space-time and smooth functions on R, which we can think of as smooth functions on the disjoint sum of the space-time and the real line. But the equations are mixing up the field at one point, the point where we are looking in the manifold, M, with another point in this disjoint sum, namely the time at which we have the oscillator variable. Okay, so it's not a local equation in the standard way of looking at these things. And there's something else that's bad about this equation, because if you actually try to analyze it, you discover it's ill-posed. There are, in fact, the only solutions you get to this equation are where the scalar field vanishes identically at the oscillator trajectory. Okay? Those are well posed, but then it's just the scalar field propagating with no other interference. Okay? So what people do, if they want to study this more rigorously, is somehow smear out the interaction a little bit, keeping the idea that the oscillator simply has one dynamical degree of freedom. So we thicken the trajectory a little bit, but that has the effect of coupling together the interaction of the field at space-like separated points via interaction with this single dynamical degree of freedom along the thickened trajectory. So it was already non-local in one sense. When we regularize it, it becomes even more non-local, if that is a reasonable comparison. But anyway, so this is an example where a non-local operator has actually been hanging around in mathematical physics for 40 years or so. Another area, and this is where we come to go beyond smooth geometry, is noncommutative spacetime models. So this comes from a paper of Lechner and Fesch. They wanted to analyze how quantum fields would respond to some non-commutative geometry. And instead of saying the whole space-time is non-commutative, the idea is that asymptotically it's just an ordinary globally hyperbolic space-time, but somewhere in the middle, something strange happens, namely the way you multiply functions together is no longer the standard multiplication, but is now some non-commutative thing. So they wrote down an equation like this. So there is a standard globally Green-hyperbolic operator, and this is a non-commutative multiplication of the two smooth functions. And then, because it's non-commutative, also, it turns out that it is a non-local deformation of the original operator. Okay, so there is one. And another would be if you were interested in delay equations. Okay, so this is well studied for differential equations. Supposing we were doing delay equations in space-time, Klein-Gordon operator with a source which is itself but pulled back through some diffeomorphism. And for example, supposing that the diffeomorphism always maps P into its chronological past, then this would be a delay equation in space-time. And it's clearly non-local because it mixes up values of the field at different points. And for amusement's sake, what if you let kappa map P into its chronological future? Then it's not a delay equation anymore, but it's some kind of, well, I call it a soft time machine, because it's not, you haven't introduced any closed time-like curves into the metric. The metric is still globally hyperbolic, but this equation, the field is actually sensing, is partly sourced by what happens in the future. Okay, so it's somehow a soft time machine model. So this is some examples, and actually, in all of them, it turns out that it's enough to study situations, partial differential operators now in inverted commas, because they're not partial differential operators, but the non-local behavior is somehow confined to a compact set K. So from now on, K is always going to be compact and topologically regular, so it's the closure of its interior. And I'm also going to follow Christian Baer's lead, and instead of defining things analytically, I'm going to define them algebraically and see if I can use that, okay? So how to define this notion? Well, there is the theorem that probably most people here know, the Petrie theorem, that gives you a characterization of linear partial differential operators of locally finite order. And these are simply the linear maps of smooth functions on a manifold to itself, which do not increase the support. It's quite a remarkable result from the early 60s, but it's apparently non-analytic definition, but actually characterizes what a differential operator is. So one can begin by reformulating that, and now I've stated this for sections of bundles, that a linear map between smooth sections on two bundles over the same manifold, this is a partial differential operator of locally finite order, if and only if the following happens. So, for any open set L, and any chi smooth on the space-time that is constant on this set L, and all smooth sections, the support of the commutator of P with chi acting on F has support in F remove L, which is a little bit complicated, but Actually, if you think about it, what do you get when you take the commutator of chi with p? You get a bunch of terms in which all of which have derivatives of chi. Okay? What we will get, because the only term that doesn't have a derivative of chi is precisely the one that you cancel when you take the commutator. So all of the terms in there have derivatives of chi, so this whole thing has to vanish on L, which is why the support you would expect is actually will never intersect L. So this is a slight change to the Petrie formulation, but in fact it's equivalent to Petrie's condition. And now I'm going to define my non-local thing in the following way. So K is now the compact set where the non-locality is. We now say that a continuous map P, linear between these spaces of sections, is K non-local if the same condition holds, but now we only require this when our set L, which is where chi has to be constant, contains K. Right? So this is the slight modification to the Petrie thing. So if K is empty, then we're back exactly to what Petrie said, and we get the usual definition of a partial differential operator. So this is the definition that we will take for a K non-local operator. And one can start deriving consequences. And the first is the effect it has on supports. So if we take a smooth section F and feed it into P, it turns out that we have the following. If the support of F did not intersect K, then the result is just supported in F. Right? So it's support non-increasing. But if the support of F does intersect K, then all you can say is that the support of PF is in the support of F union K. So it's as if suddenly if you touch K at all, then boof, you might be supported over the whole of K. So you get this sort of jump. So this comes out of that definition. Outside our region K, this is of course nothing but a PDO, so in the usual sense. And if it has a formal dual, then that is also K non-local by the same conditions. And then you can start playing games, you can start composing these things, you can take linear combinations and compositions of two of these guys with different, sorry, hit the wrong button, with different regions. Then of course it's K non-local, but for the union of the two regions for these two operators. And obviously if you have duals, then you have the obvious composition rule. So a certain amount of algebraic properties follow directly from the definition. So some examples, well, obviously all of the Green-hyperbolic operators are all partial differential operators, rather, of locally finite order in. We can include integral operators now, where the integral kernel is, for example, smooth on M cross M, but it could even be distributional. The classes that we would need is a smooth function nuclear tensor product with distributions, provided its support was in K cross K. And the reason is that if we now take some chi that's constant on a region that contains K, then multiplication by chi essentially commutes with the integral kernel, and therefore it commutes with this operator P. So we rather trivially satisfy the condition because chi commutes with P vanishes. Okay, so this certainly satisfies the condition, and this is K non-local. So we get a bunch of things. In particular, remember this operator here appeared when we tried to decouple the system of equations. And such a thing would be K non-local, provided that the R and S are, for example, partial differential operators whose coefficients are supported in K. And E plus minus are green operators. Now, importantly, this is not a pseudo-differential operator. We're even beyond that class at this point. Okay, so these are quite non-local. And of course, because of the earlier properties, I've got these examples, but also all algebraic combinations of them. So I can start putting them together, take a partial differential operator and add one of these operators like so, and it'll still be K non-local. K is still going to be compact, yes. In this, sure, but the point is that then you post-compose with R, and R is going to map smooth sections into things supported in K. Okay. Okay, this sounds a little bit restrictive, but it is actually what you would get from that Unruh de Witt detector example, for example. So it's more natural than it seems. So this support property suggests a sort of modified causal structure based on causal curves that are piecewise smooth modulo finitely many jumps between points of K. Right? So here is a causal curve going along, and if it hits K, then it can hop and go over here and then proceed as another piecewise smooth causal curve. And we now get a modified causal future and past. It's going to be the ordinary one, provided that the ordinary one never hits K. But if you ever hit K, then it can jump. And suddenly you have to build in the whole causal future of K as well. Right? So this is a modified thing. Clement, yeah. No, just in K. So to some extent, it's almost as if K is a point, right? There's a bit of a flavor to this. It's sort of a fat point, right? So if you go in, you come out of the point, fat point, but that means somewhere else in our manifold. Okay, so now we come to the definition of a Green operator for such an operator. So let's take a K non-local operator, and then we follow something very similar to the definition of Green-hyperbolicity. So we have the two solution operator properties, and then the only thing that differs is the support property. So in the usual case, you have the causal future and past, and here we just replace this by our modified causal future and past. So that's how we're going to define things, and then everything else is the same. We'll say now that this is a K non-local Green hyperbolic operator if both P and its formal dual admit Green operators of this type. We're not assuming uniqueness, and I will come to some examples later on. That's the main technical result I'll present. So just as with Bayes' definition, this is algebraic, but it has analytic consequences. And if you work through Bayes' proof, you can actually find that the fundamental result, which collect together many of the things in his paper, can be stated in the following way. All goes through for these K non-local things. So here is what I call the main theorem of Green hyperbolicity. If we take a K non-local Green hyperbolic operator, it's originally going to be defined on smooth sections, right, of these two bundles, but we could restrict it to sections that are strictly past compact supported, or strictly future compact supported, or for that matter, just past compact support, future compact support. So that gives us two restrictions of the operator, or we can extend it to distributional sections that again are past compact or future compact support. Okay? So we can consider two restrictions or one extension, and the result is that in each of these cases we actually get genuine inverses that are continuous between these spaces of functions in the correct direction. And so one of these restrictions, the tildes and bars and hats aren't all that important, but I've written the notation down, and they are continuous in the appropriate topologies between these spaces. Each of them is a successive extension of our original green operator, and each of them obeys an appropriate generalization of the support property G3 prime with this modified causal structure. And because these ones are genuine inverses to some operator, we now have uniqueness. So uniqueness has dropped out, apparently out of thin air, because everything is now uniquely determined by P. And also we get continuity of our original green operators. That wasn't assumed from the start, but has now dropped into our lap. So we actually get some analytic results out of this apparently algebraic definition. And also one can prove some other things. So these, there's almost an algebraic structure. If you have two K non-local green hyperbolic operators, then the product also has green operators. And if you have a green hyperbolic operator, then there is an exact sequence that takes us between various spaces of compactly supported sections and space-like compact supported sections. And here in the middle, well, here we have the operator itself, and here in the middle, the difference of its green operators. And this exact sequence condenses very many of the standard results about green operators into one very compact package. And I don't know if James is going to mention it, but the main thing about it is that once you've got that, you can define a symplectic structure on the solution space using this difference of green operators, at least if this is formally self-adjoint. And you can also make a bosonic quantization of the model if this operator is also real. And the commutation relations are determined by this difference of green operators. And normally that gives you commutation at space-like separation, because the support of the green operator is within the usual causal future. What happens now is that the support of the green operator acting on something is in this modified causal future, modified causal path. So now we have commutation not necessarily at space-like separation. You need to be sometimes a little bit further separated than space-like separated. Okay, so the commutation relations sense this modified causal structure, U to K. All right, so now I come to the main technical part to actually sketch how you can prove existence of these operators. And the problem we have is that these are not partial differential operators. They're not pseudo-differential operators. So you have to close Hermander and push it to the side of your desk because it's not going to help. And then you have to go back. Actually, what you need to do is open Hermander's papers from the mid-60s and see how he built it all up. You get some hints from that. So let us consider a family of non-local operators, and I'm going to start with some honest green hyperbolic operator P. And that, of course, is what I had in all those examples. And then the A of lambda, each of those, for each value of lambda, I have a map from smooth functions on space-time to functions that are supported in K. And I also require that if F vanishes on K, then A lambda vanishes identically on F. And A of 0 is going to be 0, so at that point I just get my green hyperbolic operator. And then the last, okay, two more things. I require some regularity. So there has to be some condition here, and that there are real numbers beta and gamma, which add to something strictly positive, so that the green operators extend continuously from compactly supported Sobolev functions of order S to HS plus beta lock. Okay, so if beta is positive, which is the usual situation of interest, this improves regularity a bit. Okay, And the reason for assuming something like this is that a second-order normally hyperbolic operator improves regularity by 1 degree. Okay, so this is one of the surprising things. It's not 2, it's just 1. So this is which is really the big difference between hyperbolic and elliptic operators. Okay, so we're going to assume that this thing probably improves smoothness a little bit, and then A lambda is allowed to, well, it maps from HS lock and to HS plus gamma on K, so back into this compact set K, and the effect of doing both will maybe change regularity by beta and then by an additional gamma. So overall, we get an improvement in smoothness. Okay? So don't care actually how much of an improvement in smoothness I get. The last thing we are going to assume is that this composite, that when I have my green operators for the honest green hyperbolic operator and I compose with A of lambda, I should get something holomorphic, the simplicity on the whole of the complex plane, but one could restrict, and with respect to the topology of bounded convergence between these two Sobolev spaces. And the advantage of this slight improvement in regularity is that this operator, when we now go from between spaces of the same regularity, it is compact, okay, by Sobolev embedding results. So that's the nice situation to be in. So now we come to the theorem, and I'm going to define two subsets of sets of complex numbers, and these are going to be the values of lambda at which we can find solutions to P plus A of lambda on phi equals 0 with support that is past compact or future compact. Right. So these are homogeneous solutions to this funny equation that either appear from nowhere, so in the far past they vanish, so past compact support, or they're solutions going along very happily and then poof, they disappear into nowhere. Okay? So those have future compact support. Normally, we don't imagine that we have any solutions like that when we're playing with hyperbolic equations, for good reasons. So I'm just going to let lambda be the set of values for which you do find some of these funny solutions, appearing or disappearing ones. And then what you prove is that the union of those two is discrete, subset of complex numbers, complement is open and contains 0. So we have an open neighborhood, in fact, essentially all of the complex plane, apart from this discrete set. And except in that discrete set, we actually have advanced and retarded K non-local green operators, and those are holomorphic, except on the exceptional set with respect to the topology of bounded convergence between C naught infinity and C infinity. The green operators themselves have continuous extensions with the same regularity improvement as the original operator. Okay, so it's very much the same as the original. And another fact is that it turns out that these spaces of appearing or disappearing solutions, those are finite dimensional. So almost all values of lambda, they're empty. Well, that's finite dimensional. But even when you're on one of these exceptional values, you only ever find a finite dimensional space of problematic things. So the takeaway message at this stage is that the obstruction to existence is just solutions that appear or disappear spontaneously. So if your model has any sort of energy estimate, then of course there will never ever be any such things, because the energy is 0 to start with, it'll be 0 in the future, and likewise going backwards. So, however, you can cook up examples in which these things actually are present, okay? And you can see that you get finite dimensional spaces. So, and obviously, if the hypotheses not only apply to P and A, but also to their formal duals, then we get green operators for this operator and its formal dual, so we have green hyperbolicity, except on a discrete set. So to give a quick sketch of the proof, what we do is we invert the identity plus this composite. And remember, this is going to be compact operator, and at lambda equals 0, it is in fact just, well, this bit vanishes, and so I've just got the identity. So that is invertible, and so I can use the analytic Fredholm theorem to say that I can find inverses to this for all lambda other than in a discrete exceptional set. So I can do this in some fixed Sobolev space, and then what I do is use the fact that this operator here improves smoothness a little bit to sort of pull myself up by my bootlaces and show that the same inverse that's on this Sobolev space also gives an inverse by restriction to all more regular Sobolev spaces, okay? Because the thing you might worry about is that, well, yes, you can prove invertibility in this space and this space and this space, but maybe it's not the same inverse, okay? So it is actually the same inverse because of this smoothness improving. And in fact, then you push yourself out of the Sobolev class because you can invert to arbitrarily a high order and actually get continuous invertibility on the smooth, compactly supported functions support in K. And from there, you push yourself a little bit further out and get to invertibility on functions with past compact or future compact support. And then finally, we do the following. Here is our original operator, and we factorize it because, of course, P has green operators, and this is one of these extended green operators to deal with past or future compactly supported things. So I can factor out P on this side, and then again use the fact that I have genuine inverses to this to find an inverse to this operator. So in the obvious way, I use the inverse of this operator here, and then post-compose with the green operators there. And then you show that that thing is actually a green operator for the original operator you're interested in. So that's sketch of the proof. And just a couple more things. If you look at these spaces of exceptional things, okay, the things that would be excluded by energy conditions, we can look at the dimensions, okay, and here I've got the dimension of the appearing or disappearing solutions for P plus A, and here I have the dimensions of that space for the formal duals, except I switch around whether I've got past compact or future compact. So the result here is that the dimension of the space of, say, spontaneously appearing solutions for the operator is the same as the dimension of the space of spontaneously disappearing solutions for its formal dual. Okay, so, and this also comes out of Fredholm theory. The most interesting case is when this is actually self-adjoint, in which case you find that the dimension of the space of appearing solutions has to be the same as the dimension of space of disappearing ones. It's kind of funny thing. And the proof really is to use Fredholm theory again. We're going to look at the composite like so, and then the index, which is the difference of the dimensions of these kernels here, is independent of lambda. That's from Fredholm theory. And when we go back to lambda equals 0, well, this vanishes anyway. So the index is 0 at that point. So it's constant and 0 at one point, so it's just 0. And then the rest of it is to realize that this dimension is actually the same. I think it's this one, and this one is the same as the dimension of that one. Okay, so that's how you prove this curious result on dimensions. Okay, so examples then, all green hyperbolic operators immediately fall into this setting. So the only advantage there is we control the the topology in which you have holomorphicity. So there's a small amount extra even in that case. We can now add on some integral kernels when our kernel is sufficiently holomorphic, and we can deal with operators of this form where, now let's suppose that this is the Green operator of something second order normally hyperbolic, so it improves by one order, so provided that R and S between them lose less than 1, then overall you're improving. Okay, and so you can do this. And an amusing side to that is that you can now solve these systems, not only 2 by 2, but n by n, by doing LU factorization. So you take your system and you factorize it as 2 triangular systems of matrices, okay? And for each of them, you get exact inverses, not inverses modulo smoothing operators. These are exact on the nose inverses. So you can solve systems in a rather unusual way, but a natural way from the perspective of linear algebra, but just not the way you do it from the perspective of PDE theory. So coming towards the end, here is one of the applications we have in mind. This is work in progress with Rainer Ferch. We consider 2 normally hyperbolic operators, P and Q, and some mixing term, which is in fact going to be built from a non-commutative product, or product of functions that is commutative outside a compact set K, but inside it's non-commutative. So you've got a nice space-time with something very odd happening inside K. And so now, these operators that you get by this multiplication, these are K non-local, and the hard part here is to show that, you see, ordinary multiplication would preserve differentiability, right? This thing, it is very hard to work out that it preserves differentiability, and what we were able to do after some effort is to show, well, it might just lose you an epsilon of regularity. But the epsilon can be made as small as you like, but we haven't found a way to say it exactly preserves regularity. But that's okay, because the Green hyperbolic operator, Green operators will improve regularity by 1 if it's second order. So this coupled system now is Green hyperbolic, modulo discrete exceptional sets, and because we have this exact sequence, the whole thing can be quantized. So in a very rapid way, we find a quantization of a model like this, which is very strange. And the reason we're interested in it is to imagine that phi is going to be the system field and psi is going to be a probe. But we have this, we want to see how you do measurement theory in this non-commutative setting. By the way, if that sounds a bit exotic, you can use exactly the same to do measurement theory in honest to goodness smooth space-times. Just make this ordinary multiplication, and we have a worked out theory for quantum field measurement in that setting. This is a little bit of playing around to see how that picture changes when you have a bit of non-commutativity. And I think this is the end. So the summary is that we have this algebraic notion to weaken non-locality, generalize green hyperbolicity, we can quantize, and there are non-trivial examples. So the open questions are things like, well, do you get a nice notion of a state for a field theory on this sort of thing, particularly a Hadamard state, and can you renormalize the stress tensor? Well, one can always push the mathematics a bit further. But I thank you for your attention at that point.